My goals in this talk are to promote a philosophy of extracting as much information as you can from weak optical signals, and to perhaps surprise you with very weak signals being adequate for useful imaging. This will be through two main topics. In the first half, I'll talk about active depth and reflectivity imaging with high photon efficiency, meaning that the quality is good considering that few photons are detected. In the second half, I'll talk about non-line of sight imaging. Each half will have a few related stories. Here's an ordinary digital photo of Marsh Plaza at Boston University. How many photons do you think were detected by the camera to produce it? It's a lot, and I don't really know the answer. What do you think within a couple orders of magnitude? Well done. Based on the psychology of multiple choice tests, you've correctly chosen 4 times 10 to the 12, and I have at least a plausibility argument for that choice. The illuminance on an overcast day is about 10 to the 3rd lumens per square meter. The aperture area may be about 10 to the minus 4 square meters. At the center of the visible spectrum, we'd have about 4 times 10 to the 15 photons per second to produce a lumen. The exposure time might be about 10 to the minus 2 seconds. And the camera might detect about 10% of incident photons. That gives 4 quadrillion photons. If the photo is 4 megapixels, this works out to be 1,000,000 photons per pixel. My first topic is reflectivity and depth estimates from a lot fewer photons per pixel. It's not meant to be an apples to apples comparison, but I'm talking about 6 orders of magnitude fewer photons. Here I've gathered some examples where the first row shows the result from some conventional technique, and the second row shows what we obtain with the same data. In the initial work, we had exactly 1 detected photon per pixel in a method we called first-photon imaging. This method can be effective with a signal-to-background ratio down to about 1. We subsequently looked at related problems that are more challenging in a variety of ways. Using a spat array makes it inevitable that the time resolution will be greatly coarser. In this, it's about 400 picoseconds instead of 8 picoseconds. With about twice as much signal and the same signal-to-background ratio, we get good results. We also looked at withstanding much more ambient light. Here, there's 25 times as much ambient light. The fourth column shows imaging through a partially transmissive scatterer. I'll explain first photon imaging in detail, starting with the concept of active imaging with pulsed illumination. Suppose we have a pulse-directed light source. Several properties can be inferred from the relationship between the transmitted pulse and the received pulse. The time shift is called the time of flight, and it reveals distance. The baseline offset tells how much background or ambient light is present. And the amplitude of the received pulse over the background gives the reflectivity. Scanning the light source over the whole scene gives a depth image and a reflectivity image. That's the basic idea of Lidar, and Lidar has lots of applications from A to Z. The biggest commercial driver at the moment is autonomous navigation. It's generally agreed that using RGB cameras alone is not enough to provide the robustness and accuracy that is needed for safety. The design space is complicated with issues like eye safety, range, transverse resolution, longitudinal resolution, etc. For today, I'm going to simplify all of this by saying that all trade-offs are improved by using light efficiently. That is, make the most of the light you have in both absolute terms and relative to the ambient light. To have a photon-efficient implementation, to make the most of a small number of detected photons, we would want to use a single photon detector. We have a pulsed light source that we're going to raster scan. The illumination of one small patch at a time, indexed by ij, creates our transverse spatial resolution. We'll do detection with a single photon avalanche diode. We'll also need a way to record times of photon detections with high resolution. We operate a time-correlated single photon counting module with 8 picosecond bins. An unstated assumption in most work is that a histogram of detection times over many repetitions is treated as a proxy for the analog waveform of the earlier discussion. It's in discrete time because of the finite resolution of the time tagging, and it's noisy. But a histogram starts to seem like a silly concept with just a handful of detections, so forming images from so few detections seems unreasonable. One of my main points today is that it's not unreasonable to get by with fewer photons than are needed to form a reasonable histogram. It's maybe just a slight change of perspective, but we want to think about individual photon detections rather than the properties of the histogram. Time-correlated detection puts the illumination and detection on a common time axis. From the quantum nature of light detection, what we're actually seeing is an inhomogeneous Poisson process. The rate function of the Poisson process, in the absence of background, is a scaled and time-shifted version of the illumination waveform. It has a time shift depending on depth Zij and amplitude alpha ij of the patch ij. The contribution from background light and dark counts is a homogeneous Poisson process. So we have a merger of these Poisson processes, adding together the background and the response from the scene. Not every incident light pulse generates a photon detection. Suppose there's no detection from the first illumination repetition period. There may be no detection in the second period as well. And then suppose there's a detection in the third period. Here that detection is shown at a relatively likely time where the yellow flux waveform is high, so the detection is colored orange as if we know that it's from the scene response. Another possibility is for the detection to be in the third period, but at a less likely time, meaning that it's due to background. But this function in yellow is not known. That's part of the actual problem. When you see a detection, you don't know if the rate function is as shown here, or instead, the rate function is as shown here. The time shift is part of what you're trying to infer. So it seems difficult to get much from a single detection. Let's suppose we follow the strategy of sending illumination pulses at pixel ij until we have our first photon detection. Then we have some number kij of pulses until that detection. For that detection, we have a detection time relative to the time of the last pulse emission, which we call Tij. The number Kij is random, with a geometric distribution that encodes the reflectivity alpha ij in the sense that it has a parameter that has a one-to-one dependence on alpha ij. Similarly, the detection times encode the depth Zij. Each detection time is drawn from a PDF equal to a normalized version of the pulse plus background rate function depicted in yellow on the previous slide. We can hope that when we exploit some reasonable model of nearby pixels usually having similar depths and reflectivity, these observations are enough to solve an inverse problem for the depths and reflectivities. Nature has been kind to us in that the negative log likelihood of Kij is convex in alpha ij and has no dependence on Zij. Nature is less kind in the Tij distribution. If there were no noise, under reasonable approximations of laser pulse shape, we would have convexity of the negative log likelihood, but as it is, we do not have convexity. The image formation method that we developed follows a three-step procedure. First, compute a regularized maximum likelihood estimate of alpha, exploiting the convexity here and adding a convex regularizer. Then, because we want to be able to make believe that there's no contribution from background, we do our best at censoring noise detections. Finally, we compute a regularized maximum likelihood estimate of Z using the negative log likelihood ignoring the background. Notice that we're exploiting the tractability of convex optimization by massaging the problem into using convex optimizations. The reflectivity part is no problem, but for the depth part, we need to censor to make believe there's no background, and we approximate the pulse shape so that its negative log is convex. Following the data collection protocol I described, we have one detected photon per pixel. I'll show results where about half of those detected photons are due to ambient light and dark counts. First, here's raw reflectivity information overlaid on the 3D point cloud. We rotate the model so that you see it as 3D, but this is imaging from a single vantage point. Obviously, this is very noisy. The result of that first step gives significantly more accurate reflectivity. It's rendered on top of very noisy depth information, so it only looks strikingly denoised from a straight-on front view. You can see from that view that you can read the text, so it's greatly denoised. Now here's the result of step 2. You can see that our technique doesn't do a perfect job, and as you might have guessed, most of its mistakes are near the depth discontinuities. Still, this is a big improvement upon the result of step 1. And here's the result of the third step, which is our final reconstruction. Now, before switching to a different sort of weak signal, I'd like to tell a couple of related stories. In first-photon imaging, and even more so in the subsequent work that withstands very high ambient light levels, the reflectivity estimate is important to noise censoring, which is important to the depth estimation. So let's examine the Lidar reflectivity problem further. By having periodic illumination and low flux reaching the detector, we have repeated trials in which either one photon is detected or no photons are detected. So we're observing a Bernoulli process, and the parameter of the Bernoulli process relates to the reflectivity of the scene patch. A conventional system observes a fixed number of trials, which generates a binomial random variable. First photon imaging observes until the first success, which generates a geometric random variable. If we observed until the nth success, where L is some fixed number, we'd have a negative binomial random variable. Even in a Bernoulli process setting, where the trials are independent, there is something to optimize here, and it gives us a sort of free lunch. Optimizing the data acquisition is equivalent to choosing a connected rooted tree. A couple of examples are shown here. With each trial, there's a step down, either left or right, based on heads or tails, or detection, lack of detection. To have a fixed number of trials is to stop at a fixed depth, which gives a binomial observation. To stop at a fixed number of successes looks like this, which gives a negative binomial observation. A simple online adaptation achieves an oracle bound, and that oracle bound gives a multiplicative reduction in mean squared error that's a lot like a coding gain in source coding. Quantum electron microscopy is another setting in which we've studied acquisition strategies and found that a simple stopping rule can make a big difference. Suppose there's a binary valued sample that's placed in one arm of a Mach-Zehnder interferometer. Then when the sample is absent or transparent, constructive and destructive interference cause an electron to be detected at D1. When the sample is opaque, then there can be a detection in any of the detectors with these probabilities as shown. In particular, a detection at D2 is definitive information on the sample being opaque, even though the electron could not have struck the sample, since it would have then not made it to D2. That's a quantum spookiness. The term interaction-free measurement comes from applying multiple stages of the sort shown at the top, which approaches surety in whether the sample is opaque or transparent without any damage to the sample. We've shown that an adaptive acquisition approach makes even a single stage useful. The plot here shows probability of error as a function of the mean number of electrons absorbed by the sample, with and without interaction-free measurement, and with and without the scattering detector D3. Whether or not D3 is present, there's an improvement from IFM. The take-home messages from this part of the talk are that fine-grained statistical modeling can make a few photons or electrons informative enough to do interesting things. And even very simple particle-level models can be the basis for processing that improve substantially over conventional methods. Now I'll shift our attention to non-line-of-sight imaging. We've termed this computational periscopy because it builds a periscope using computation instead of mirrors. So far, we've been talking about line-of-sight imaging. This can include heavy computation, but it certainly doesn't have to. What if there's an opaque surface between the desired scene and your camera? You could see around the opaque surface if there were a mirror on the wall. But if it's not a mirror, you're just seeing the wall, wishing it were a mirror. We'd like for computation to somehow make it possible to use that matte wall as if it were a mirror. Why might you care to do this? It gives a capability that you could call asymmetric vision, because I can see you while you can't see me. It also could be useful in autonomous navigation. For example, you might see a pedestrian that's hidden by a parked truck. Why can't you normally use a matte wall as if it were a mirror? At a diffuse surface, incoming light scatters in all directions. Reciprocally, when you look at a point on a diffuse surface, the light has come from all directions. As shown in this illustration, you can't tell that the scene has two bright regions because the blurring is severe. You need some mechanism to keep light paths separate. Previous methods for non-line of sight imaging separated light paths by their lengths using time of flight. So there had to be an active illumination and very precise time-resolved sensing. That's a difficult and expensive proposition. We introduced the simple idea of light paths being separated by incidental occlusion. If there's an occluding object, then it casts shadows in the camera field of view. More precisely, since the light is coming from a distributed area rather than a single point, we don't have a sharp shadow, we have a penumbra, meaning regions of partial shadow. Remember that this is in contrast to a setting where there is no occluding object. In the ill-posed case on the right, the measurements y can be expressed as a linear operator applied to the scene of interest, represented by f. That linear operator is hopelessly difficult to invert. With the occluding object, there's again a linear operator with parameters that depend on the location of the occluding object. This is not hopelessly difficult to invert because of the separation of light paths by the occluding object. Shown here is our real-life experimental setup. The hidden scene is displayed on a monitor so that we can easily have many different hidden scenes. There's an occluder in an unknown position. And we take a photograph with an ordinary digital camera. Shown here is a bright, colorful scene and no ambient light, but we'll see that we used experimental data that's much more difficult to interpret. From our photograph Y, we wish to estimate the occluder position P0 and the hidden scene F. This figure renders real experimental data, and you can see that the penumbra is soft and blurry with no clear gradations of hue. A rather simple reconstruction approach yields an accurate, though low resolution, view of the hidden scene. The first step is to estimate the occluder position through simple linear algebra principles. We choose the P0 that maximizes the orthogonal projection of the measurement to the range space of the forward operator. Then, the image formation is a simple total variation regularized inversion. Several results are shown here. The last two rows show that occluder position P0 being unknown has little impact on the reconstruction quality. The first two columns highlight that two measured penumbras can look very similar to the naked eye and yet contain the information necessary to reconstruct distinct scenes. Now, before I close, I'll tell a couple of related stories. Our use of occlusion was preceded by the corner camera of K.D. Bauman. Bauman et al. Point a video camera at the floor next to a vertical edge and use a sequence of frames to extract 1D traces of large moving objects of different colors. A single frame of the input video can appear to have no non-line of sight information in it. Using multiple frames, they build on change magnification ideas that have been developed in Bill Freeman's group over many years to achieve these results. We've built upon this idea to show that one can use a single frame to produce two-dimensional scene estimates. The panels here show slight performance degradation from left to right as the signal to background ratio is reduced. In the rightmost column, it's hard to perceive any yellowness or blueness variation, yet the reconstruction is quite accurate in both angular position and range. Finally, Exploiting a single vertical edge can be combined with exploiting time of flight. In edge-resolved transient imaging, the illumination is moved along a small arc, illuminating larger and larger fractions of the hidden space. With a SPAD detector focused on a patch near that arc, we have an approximately coaxial geometry. Differences between successive histograms give an approximation to illuminating a single angular wedge. Analytical models for the response from a single facet are combined with a Markov chain Monte Carlo estimation algorithm to give us scene reconstructions of the full hidden space despite having only a very small aperture into that space. To summarize the second part, occlusion can be a powerful and useful concept. It's made me never look at shadows the same way again, and I hope you'll say the same.